webinar today will be presented by two speakers, both affiliated with SUNY-ESF. Dr. Mark Eisenbies has over 15 years experience in forestry, soil science, and hydrology, and earned his PhD in 2004, evaluating long-term productivity. He has been working with the Willow program at SUNY-ESF since 2011 on harvesting logistics, feedstock quality, and other projects. Mark won't be speaking during the main part of today's presentation, but he's a major contributor to this work, and we're very glad to have him standing by to address any questions about the analysis presented here and the information specific to chip quality. The contributor we'll hear from today is Dr. Timothy Volk, who has over 25 years of experience working in the fields of forestry, agroforestry, short rotation woody crops, bioenergy, and phytoremediation in the northeastern United States and West Africa. He's currently a senior research associate at SUNY-ESF in Syracuse, New York. Mark and Tim's presentation today will focus on issues of productivity, efficiency, and quality related to short rotation woody biomass harvesting. So at this point, I'll turn it over to Tim to get things going.
Okay, thanks Sarah for pulling this together and making all the pieces work. So we're going to walk through some work that we've been doing here for the last number of years and sort of provide an update on where things are at in terms of harvesting of willow biomass crops. Also talk about chip quality and what we've been finding in terms of what the quality of willow chips is when they're harvested at a large scale as opposed to coming off small scale yield trial type harvests. We'll have a few comments here on economics as well in terms of what improvements have been made over the last few years as this harvester has been developed. Okay, so up front, just to acknowledge that funding over the last few years for work on willow harvesting and chip quality issues has come from a number of sources: Department of Energy, NYSERDA, NYSTAR, USDA, and the New Bio program as well. And there have been some key partners involved in this project over the last number of years. New Holland has been a key partner. It's really their harvesting system that we've been working with primarily over the last few years. Greenwood Resources is out in the Pacific Northwest, and they grow hybrid poplar on about 30,000 acres out there. For some reason, Zeachem's label in the bottom left has disappeared, but they're the biorefinery that Greenwood is working with here, and we have worked with Applied Biorefinery Sciences. This is an organization here trying to develop biorefinery approaches here in the Northeast using woody biomass. Mesa Reduction and Engineering does a lot of work in the biomass realm in the Northeast and other parts of the country, particularly around pre-processing and logistics. Okay, so just a couple of slides to sort of bring people up to speed on where things are at with willow deployment, particularly in relation to the USDA Biomass Crop Assistance Program. So this slide just shows you the 3 counties in northern New York where willow is currently deployed, and there's about 1,200 acres of willow under that program. As part of the new bio program, there are willow trials in a number of other states and areas as well, but in terms of commercial scale-up production, this is where activity is currently focused on. This just shows you a little more detail what's going on in those counties with the green dots showing you where willow fields are located. And then the 2 outlets for this material are both owned by a company called Bioenergy. Bioenergy uses wood to produce renewable electricity and heat at these facilities. And they have signed agreements with all the landowners involved in the BCAP program to buy all the willow from these fields over the next 10 years. So a recent development that was important and is important for both bioenergy and short rotation woody crops in this region is a long-term contract that was signed between the Defense Department and Bioenergy Black River. So just go back, that's this facility here, except for the arrow's not working. Oh, there it is. So this facility here, which is on the base, Fort Drum Base, they've just signed a 20-year agreement to provide renewable energy here to the Army in a contract arrangement. So that will provide some degree of certainty for the bioenergy market here in northern New York, and hopefully provide some opportunities to grow the bioenergy and short rotation woody crops market here in this region. So this is the largest renewable energy contract that the Army has signed to date, and they have a fairly aggressive program to get a significant portion of their power and energy supply from renewables in the near future. Okay, so just to focus in on Willow now a little more, and just to remind people, many people on here are probably familiar with this cropping cycle, but just to go over it again so we understand how the system is working. This is how the system generally works. We start with site preparation on open agricultural land. It's prepared and then planted using unrooted dormant cuttings. Typically after the first year, it's coppiced or cut back. It sprouts back after that establishment year after being coppiced and grows back fairly rapidly, right? And then we typically go up here to a 3 or 4 year cycle, and it's time to harvest. Harvest is typically done in the late fall or winter. The product is coming off here and then being delivered to end users, and the crop sprouts the following spring, grows for another 3 to 4 years, and then we have 7 of these crop cycles on the green arrows, and each time we're harvesting, we're pulling off biomass and selling it to an end user. So that's the general process that we're looking at here in terms of how willow is being grown and being managed. And then today we're going to focus really in on this harvesting piece, what's happening with harvesting and the quality of the chips that are being produced from these harvests. So just a couple of quick notes on why the focus on harvesting has been fairly intense over a number of years now. It's really the single largest cost. So if you go back to this diagram and think about the fact that you have 7 of these cycles, which means this equipment, whatever is being used for the harvesting operation over the lifespan of this crop of 20 to 25 years, is being put on the ground 7 times, in contrast to, for example, planting, which is a one-time operation. So it's the largest single part of the final cost of willow biomass delivered to an end user. It's also harvesting is also the second largest source of greenhouse gas emissions after nitrogen fertilizer additions in these systems. So it's important from a number of different perspectives, and something that requires attention and focus in order to make improvements on it. There are multiple ways of approaching harvesting of short rotation woody crops, and there's been work done in other parts of North America and quite a bit of work done in Europe over the years. And so these are just some examples of other activities that are going on in relation to harvesting willow and other woody crops. There are whole stem harvesting systems. So in the top right you can see a whole stem harvester with material that is just cut off and piled and then dropped on the ground and then moved to the edge of the roadside. So these pieces of equipment can generally handle larger stems. You've got some potential for natural drying of the material. However, you have additional handling steps involved in these kinds of processes. Down at the bottom right, there's other folks that have worked on, instead of handling loose stems, which with willow can be a bit of a problem because of the way the material falls and can become intertwined. Baling or bundling systems. So down on the bottom is a bio-baler that was developed by folks up in Quebec and has been used in a number of different locations. There's also a bundling machine that was developed in Europe. Again, potential for natural drying, a little lower generally productivity, some benefits in terms of using these at smaller scale operations, and then just the realization that you have an extra handling step if you're going to get this material into a form that's usable by producers or end users of your product. So the focus that we have here has really been on cut and chip systems, and again, there are multiple different types of cut and chip systems. There are tractor mounted systems in the top. These two pictures here show you a couple of different tractor mounted systems. One is a modified corn chopper, and the one at the bottom is a tow behind, a forage forage harvester that folks in Quebec are now looking at. So there are other types of systems that are in play and are being developed. New Bio will next year have one of these tractor-mounted corn chopper systems here and available for use, so that will provide some benefit for smaller scale trials in particular, and also help us to get a better handle on what costs are associated with running those operations. Generally, these cut and chip operations have the advantage of that, well, as it says, you're doing the whole thing in a single process. So in one pass, you're cutting the material off and you're chipping it and then blowing chips into some sort of a collection vehicle, and those chips can then get moved off the field directly to an end user or into short-term storage. So just to have a brief summary of what's gone on here in the U.S. in terms of trying to develop willow harvesters over the last number of years. Here is the type of system that was being looked at early on, and there were a number of challenges over these sort of development periods. You can see the quality of this material and these photos that came out of some of these early harvesters was not at all acceptable. So in these pictures here, you can see that this is not material that most end users are going to be excited about getting at their facility. It's going to cause lots of problems with handling and delivery. There were problems with equipment reliability, high costs, the size of stems that could be cut and processed with some of this early equipment were also issues. So that picture, or that machine is the same as this one. It's called a bender. This is a track-mounted machine that we worked with for a number of years. It came out of Europe, out of Sweden, and some companies that were developing it there. We worked with Cornell University for a number of years to try and get that to function effectively here, and it never really did, never was reliable or produced consistent quality chips. The next step was actually New Holland contacted us and wanted to see if their forage chopper could operate in willow, and they brought a modified corn head up, and we put that through some willow and thoroughly ruined it within a few acres, but it did show the folks at New Holland that their forage chopper with no modifications on the inside could take in willow and produce a nice product. The next stage in the process was to adapt this very heavy duty header from a design in the UK. It was modified and redesigned slightly to fit on a New Holland machine. And that worked for a number of years. It had some issues with feeding, but was a significant improvement. And then finally, over the last number of years, New Holland has developed their own coppice header that fits on their forage chopper, and that's really now the focus of the work that we're doing, and will be the focus of the conversation for the rest of the webinar in terms of data we've collected and where the status of that harvesting system is at. Okay, so this is just to give you a little bit of idea about the harvesting equipment used in this project. Again, it's based on the New Holland forage choppers. So this back part of the machine, the forage chopper behind the header in this direction, there's nothing dramatically changed in this. There is some extra guards you want to put around the window, and they put a guard underneath so that lines and things don't get caught when you're cutting woody crops. But other than that, there's no significant changes to this machine. This header then fits on the front, and you can interchange and use your forage harvester for other operations, as you can see in the bottom, for either corn or grass or other operations like that. So one of the advantages of this kind of a system is that farmers can use it to harvest crops in a more traditional crops, change the head, and then harvest woody crops after the typical crop harvesting season is over. Over a number of years, we worked in conjunction with New Holland on the development of this machine. New Holland really did the work on designing the cutting head and any other modifications to the harvesting system per se. There was lots of work done on components. This is a picture that shows the front with the saw blades at the front. into the feed rollers here. They did work on these vertical rollers, how to collect material, how to get it to move in smoothly into the harvester. There was a fair amount of work done on this push bar that sits out in front of the machine. It's the first thing that comes in contact with the willow, and angle of that and the strength of that is important. A lot of work on saw blades in terms of what is the optimum type of saw blade for cutting effectively and efficiently without having huge maintenance costs incurred in the process. So what really happened here is New Holland folks would make modifications and improvement. We go out in the field and do testing, and we do monitoring around those operations. They'd learn lessons and go back and make changes and improvements, and it was an iterative process over a number of years to get to the stage of where things are at now. So we're going to show you a short little harvesting video here to give you an idea of what this looks like when it's running in the field. So this was part of harvesting operations that occurred in 2012 and 2013 in central New York. So this is a shot from inside the cab. So again, this is a single pass cut and chip system, so it's cutting off the willow. The stems are fed through the forage harvester, and it blows out chips into a collection wagon. We looked at a number of different collection wagons in this process. The one going across the screen is actually used in bean harvests, green bean harvest in upstate New York, a self-propelled wagon. This red wagon that you've seen in a couple of shots is actually a sugarcane wagon, so it was brought up from down south. It fits well into the spacing that we have for willow, and the other advantage is that it lifts higher than most of the forage dump wagons that are used in the dairy industry around here, and so you can dump directly into trucks such as you can see here. Okay, so that just gives you a little idea of the operation of the machine. So what have we found over time here as we've worked on this? This just gives you an idea of some of the different harvests that were done over a 3-year period. There were 8 different willow biomass crop harvests that were monitored using that sort of iterative process with New Holland, and also 5 hybrid poplar harvesting trials. The harvesting of hybrid poplar is not going to be something we're going to talk a lot about here. That was all done with Greenwood Resources out in the Pacific Northwest. So when you look at this kind of a graph here that has effective field capacity, I'll go over these terms again in a minute. So this is really, you can think of this as speed or hectares per hour, and this is throughput, effective material capacity, so wet tons of material coming out of the harvester per hour. Right, one might look at this and think that there's some sort of relationship here between speed and throughput of the machine. The reality is that a lot of these trials down here early on were really in the development stages of the process, and not really, the harvester was not working at the potential that it was after 3 years of focused development. So when we look at the results that we're going to discuss here in terms of harvesting productivity and what its relationship is to different characteristics and willow chip quality, we're really going to be focusing on these last 2 harvests that are highlighted here at Groveland and Auburn, 2 sites in upstate New York, where the machine was running fairly effectively after 3 years and provided the best data and also the largest amount of data. There's about 150 acres that were harvested here. When we talk about economics, we set up this base case, and this was a trial down here at Lafayette that was done in 2010. So when we come back to the economics and we talk about the base case, we use data that was collected from the harvesting back here in 2010 to indicate what the status or what the costs were associated with the machine at that point in time, and then to look at improvements that occurred over the 3-year period of this project. So let's move on, and we'll talk about what results were found from these Groveland and Auburn harvests. So just to give you a snapshot of these sites, So there was a collection of fields here and one smaller one, and this material was delivered over here into Auburn onto a hard pad. Here at Groveland, the fields were here, another set of fields here, and then they were delivered down here to a nearby farm and put into short-term storage. Again, about 150 acres were harvested in 2012 and 2013. So I don't want to get into all the details of this, but there was a lot of data collected, well over 1 million GPS data points. We had GPS equipment on the harvester and on the tractors that were hauling wagons or trucks that were collecting chips, and so we put all that stuff, all that information together, and Mark did an incredible job of processing all that information and making sense out of it, and I'll show you summary results from lots and lots of work to get that done. But again, the main things we're looking at here are ground speed, that's called effective field capacity, so how many hectares per hour. We have records now of standing biomass, wet tons per hectare, and then we have effective material capacity. You can think of that as throughput, how many megagrams wet per hour are coming out of the harvester. As a result of the work that was done and the monitoring was done, we also have information on turn times and delay times and other information like that that we won't necessarily get into all those details today. So again, just these parameters, these different components are linked, right? So again, effective field capacity, hectares per hour, standing biomass, and effective material capacity are related to one another, and all information that we collected and processed out of these harvesting operations or trials. Okay, so we could spend a lot of time talking about that process, but really this is the key summary graph. So what do we have here? We have standing biomass in terms of what was delivered. So this standing biomass number does reflect what came off the field and what was delivered to the scales at short-term storage. Again, we're doing this in wet tons because that's the way it's coming off the field, so wet tons per hectare. And on the y-axis, we have effective material capacity or throughput. How many wet tons of biomass are coming out of the machine per hour? And what we really found is that there's this two different patterns in this relationship. When you're below about 45 wet tons per hectare, there's a relationship between standing biomass and throughput. And so this is really limited by the speed that the equipment can go across the field. And so you end up developing this relationship. When you get above this about 45 wet tons per hectare mark, then the output of the harvester actually begins to level off or have a slight, a much smaller increase as the standing biomass increases. And so what you really hear is starting to reach the capacity of the machine, and it becomes more limited by the vegetation and the amount of biomass that you actually have standing on the site. We didn't have parts of these trials with more than 100 wet tons per hectare, so there's questions out here about what goes on, and at some point we would expect that we're going to reach mechanical limits for this machine and its productivity is going to drop off. So when you have these stands and you have decent stands of willow above this 45 or so wet tons per hectare, you have fairly consistent throughput with the harvester. So that's helpful in terms of trying to understand the dynamics and the costs associated with these systems. Okay, so this is from 150 acres of willow harvest, right? So this graph in the bottom is the one I just showed you in more detail on the slide, the previous slide. One of the things that is clear is that this slope can change. So this part of the graph here can flex up and down, as well as the height of the where this levels off in terms of the throughput of the machine. So this part of the graph also has the potential to slide up and down. So it's factors like the operator in the machine, the capacity of the machine, improvements to the machine, the type of ground conditions that you're dealing with may well change the dynamics or the exact location or slopes and angles of these fields. So as more data is collected, we'll have a better idea of refining that. We've already seen some shifts in some hybrid poplar plantings where this bar here tends to be shifted a little bit to the left because of the ground conditions and the type of crop conditions they're dealing with in those harvests. We also did some work to look at the system, and as we mentioned before when we were looking at the video, there were a number of different harvesting collection vehicles that we looked at. The two that were probably the most effective were this cane wagon, and landowners are now using these for harvesting in northern New York. And on one of the fields, the conditions were dry enough that we were able to put silage trucks directly into the field. So these are the kind of trucks that people also use when they're harvesting corn silage if ground conditions allow, and the spacing actually in the willow field allowed these trucks to go into the field for the most part, and we could collect directly into these trucks, and then those trucks could go off directly to short-term storage. So you skip a step, because if you collect in these cane wagons or some of these other wagons, you then need to unload into these silage trucks, which were taking the material to short-term storage. So this is a summary graph that shows what happens when you put the whole system together. So previously we were showing you numbers here, harvester operation in the field. Okay? And what this shows you now is what happens when you start adding other components in. So how about when you start adding in delays in the field that are caused by either the harvester or the tractor? What happens when you put in turns at the end of the rows associated with headlands? And we can tell you that the headlands in these trials were wholly inadequate. 10 to 15 feet to turn around this kind of equipment at the end of a row is wholly inadequate. And I think people have learned lessons, at least the people involved in these trials have learned lessons that bigger headlands has got some real value when you get to harvesting. And then what happens when you get it to the landing and move it into vehicles and deliver it to short-term storage. Okay, so those are all the steps in the process here that we have information for. What we have here is the two sites. The top site is Auburn and the bottom site is Groveland. Some differences within the operations because of ground conditions and different types of equipment, but in general you have this almost 2/3 drop in productivity of the system as you move from what's coming out of the spout of the harvester, put all the pieces together until the point of where it's being delivered to short-term storage. So lots of places through the system where you get declines or drops in productivity because of different components. So I addressed one of those already. So this drop that occurs here associated with headlands going from operations in the field down to where headlands are involved. There's a significant and fairly dramatic drop in these trials in productivity. Again, in these trials, the headlands were very inadequate, and it's helpful to have this information, and in addition to have some first-hand experience, have some other people have some first-hand experience in harvesting operations to convince them that taking an extra 15 feet and making a 30 or 35-foot headland is well worth it when you get around to harvesting. Yes, you take some little bit of land out of production, but in terms of the loss of your harvesting efficiency, small headlands clearly have a large impact. The other big piece is then getting it off the field at the landing and delivered to short-term storage. And so it's really these components that we see now are where the biggest gains are going to be made in improving overall efficiency of harvesting systems, in addition to addressing costs and further trying to get them lower or more consistent. There are some gains that still can be made at this end with the harvester and improvements to it, but as you will see shortly, we've made significant gains in terms of the costs and efficiency of the harvester. Okay, so just in terms of the efficiency, when you look at what's going on here in the field, so at Auburn, over 90% of the runs that were recorded with data, 90% of them were over 85% efficient, and in Groveland it was slightly under 90%. But generally over 85% efficient in terms of operations in the field. So not a lot of downtime associated with either the harvester or tractor-induced delays at that point in the system. When you add these other components in, and very few of the runs, about 10%, 10 to 14% of the runs had greater than 85% efficiency. So this really just to emphasize that it's these parts from the head, including the headlands and getting the material off the field and delivered to short-term storage or an end user, is where the gains are to be made, and work needs to be done to make improvements. Okay, so just a comment about harvest residues. People often wonder what's getting left behind, and this picture sort of captures the components. There are pieces of stem that sometimes don't get picked up by the harvester. There are collections of stems that are sometimes pulled along with the harvester and dropped in the field. There is lots of fine and small material that is also left behind. And sometimes there are pieces of stems that don't get cut off and are left on the stool, not illustrated so well here in this picture. But we looked at these different types of material, and I don't want to spend a lot of time on them except for that this one at the bottom, these shakes, this is really the small fine material. So the tips of branches on the willow, less than 1 to 2 millimeters in diameter, that are often knocked off when the plant is cut and dragged and pulled into the harvester. So how much stuff is left behind? About 6 to 8% of the standing biomass from the data that we collected out on these harvested fields seems to be left behind, and about half of that is this shakes material that I was mentioning. So it's this small tips and fine branches of the willow that is being left behind. And when you start looking at that material, it's probably a good idea or an acceptable idea that that material is getting left behind. It generally is harder to chip that material and get it to a consistent size, and so it often can cause some problems with handling systems. It's also got a higher nutrient content, and so leaving some of that material back behind on the field also has the potential to address some of the concerns that get expressed sometimes with nutrient removal. So really, what are you looking at then? Maybe 3 to 4% of the standing biomass gets left behind in larger pieces of material that would otherwise be nice to be able to collect. So a relatively small amount of material being left behind in these harvesting operations. Okay, so let's talk about economics for a minute in terms of this harvesting system. And again, I'm going to go back to what I mentioned before. When we were doing this work, we were required to develop this base case scenario. So in 2010, we went out and did some measurements during a willow harvesting operation. And the data that was collected at that point in time with the state of the harvester as it was and being operated is our base case scenario. It was also a slightly different collection system than what we're using now. So it had a forage harvester. Chips went into a small dump wagon that was pulled by a tractor. That small dump wagon was then unloaded into a blower, a forage blower, and those chips were then blown into a chip trailer. The advanced case scenario is the other one that we'll look at in contrast. So this is based on the harvesting data that I've been talking about from 2012, 2013. It's got a forage harvester. It's got this cane wagon that I've shown you pulled by a tractor into a silage truck, which is delivered to short-term pile. It's then reloaded and put into a chip trailer and delivered to an end user. Okay, so just some comments on this. This is actually, we collected data in the field and then provided it to folks at Oak Ridge National Lab, and they ran it in their IBSO model, and it was based on our 800,000 dry ton per year biorefinery operation in upstate New York. The willow was harvested from October to early April, and so that means that about half of the year's supply, 400,000 dry tons, was coming from willow. The other half of the material was going to come from forest residues in this scenario. When they looked at land availability and where willow could be sourced, it had a radius of about 28 miles around the facility in order to reach that target of supplying 400,000 dry tons per year. Okay, just some other comments on these things. So again, this base case is based on field data that we collected in 2010. The harvester efficiency was fairly low. It was only 74% efficient, and its speed was lower than what we've had in the last couple of years, about 1.5 miles per hour. And I talked to you that this blower was being used instead of being going directly into silage trucks to short-term storage. In contrast, you can see at the advanced case, so 3 years later, right, considerable improvements in harvester efficiency and speed. And so these really reflect the iterative process that went on over a number of years and improvements in the harvester operation. Okay, so here's the results in terms of these numbers are reported in terms of dollars per dry ton. If you just want the bottom line, here it is. In the base case scenario, costs were around $52 for harvesting, for the harvesting and logistics part of the system, $52 per dry ton. In the advanced case scenario, it's down around $34 per dry ton. So about a 35% reduction as the harvesting system was improved. And you can see where the main improvements are. Had to do with the operation of the harvester, an improved operation, better efficiency, better throughput. So that has a big impact on the costs of the harvester, and then also it has an impact on in-field transport, because if you're able to move this harvester more efficiently with less downtime, you have a lot less downtime and sitting around with collection vehicles and extra costs associated with that when things are not being productive. A little bit different in handling, and part of this is probably related to the changes in the handling system that were involved there. That forage blower, although a nice idea and at a small scale might be beneficial, it's a slower process than the other one that was used later on. So that's the sort of improvements that were made as the harvester was improved over the last several years when looked at in a scenario for a large-scale biorefinery. So that's not what everybody wants to look at. If you want to look at harvesting costs on a smaller scale, so as a producer or somebody who's managing a few hundred or a couple thousand acres, what are the costs going to be? And this is the model, a cash flow model that we've developed here at ESF. And Justin Heavey has done a lot of work in the last few months to really dramatically improve this. We've just released version 2, and we'll be doing a webinar on this in more detail later. But if you really wanted to look at producer scale type assessments of willow costs, including harvesting, this is probably a better model to use as opposed to that large scale logistics model, which is really looking at it from a biorefinery point of view. But I'll leave detailed discussions of that. You can either join us here at this short course on November 18th or 19th, or we'll be doing a webinar to walk through the updates and improvements to EcoWillow 2 as a new bio webinar in February. Okay, so the last thing I just wanted to touch on then is what about chip quality? So here's a picture of chips being unloaded at the Auburn harvest. So where are we at in terms of chip quality and concerns about that? This is an important piece to spend some time thinking about and focusing on, because if we can harvest material off but it doesn't have the quality that end users want, then it's not got the value that is needed to make the system work. There's been a lot of focus in the past on just driving down the cost per ton and not being concerned about the quality of the material, but if you have low cost material that's low quality, it's not going to work in the system very well. The other thing that has come to light fairly clearly in the last few years is that there's real differences in the quality of hand-harvested, research trial, pristine material versus field-harvested large-scale types of harvesting of material. One of the biggest items that is noted in that is increased variability when you go to large-scale harvesting. And Kevin Kenny and others wrote a paper in 2013 that showed this fairly dramatically. And here's a graph that shows you ash content for corn, miscanthus, and wheat. And so you can see, for example, here's corn stover, and people often talk about corn stover having a 7 or 8% ash content, and that's certainly what looks like the majority of the samples are here. But then you look at this and you realize they are getting in a significant number of samples that are over 10%, and then even samples out here that are above 39% ash content. So as an end user trying to build a facility to run on a source of feedstock, this kind of uncertainty of what the quality of the material is going to be causes a lot of problems. And if you've designed your system to run on 7 to 9% ash content of the material come in, and you get truckloads of material that's 20 or 25% or more ash content, it's going to cause a number of problems, both in the efficiency of the operation and how the system is going to run, as well as wear and tear. So when you go to large-scale harvesting, this is one of the big issues, the increase in the variability. So we took that idea and looked at it, and we'll show you those results in a minute. The other thing that is out that I think is important when we talk about quality of material is these standards. So ISO, the ISO 17725 standards have come out for solid biomass. They have them for any number of types of solid biomass, pellets, and the one here that I'm showing you is focused on wood chips. So that's the one that we have keyed in on when we compare Willow. Does it fit the quality standards that have been outlined in these ISO standards? And these ISO standards are really largely based on work that was done in Europe over a number of years, but now have been adopted by the International Standard Organization. Okay, so this is, I don't expect you to read this, but this is just an idea of what the main table is in the ISO standards for wood chips. We're just going to focus in on a few of these parameters: moisture, ash content, energy content, and particle size distribution. So there have been a lot of concerns about this in the past related to Willow. There's some misunderstanding about these components, particularly moisture and ash content with Willow. Particle size has been an issue I showed you early on. Some of the early harvesting systems had real problems producing a consistent size chips, and those, surprisingly, those impressions have lingered for years and years. This is just a paper that actually just was released this morning that has this data in it in more detail. So on Bioenergy Research, if you're interested in looking at it in more detail, it's now available online with the data in it and summarized. I'll give you the key messages here. What we have here is moisture content. And we have two things. We have pristine samples, so we actually looked at samples from hand-harvested yield trials at 2 locations in central New York. That's what the black bars are. And here's mechanical harvested. So this is moisture contents from samples that were collected off the back of trucks when the material was deposited in them and delivered to short-term storage from the harvest at the 2 sites in Auburn and Groveland. So you can see there is some distribution and variation here, and that's important to note and be aware of. The mechanical mean was a little lower than the pristine mean. This is often the range that gets reported for Willow biomass. People often report 50 to 55% in the literature. Certainly in terms of mechanical harvesting, that's not the kind of moisture content that's coming off of these fields. There are some other factors related potentially to weather, but likely as you harvest the material and chip it and blow it through this machine, there may be some initial drop in moisture that's occurring in the mechanical harvesting operation. So I should just comment, there is no ISO standard for the type of chips that we were working with. They're Class B chips because of the fact that they're coming from short rotation coppice. So in the ISO standard, you're just required to report what your mean moisture content is. Mean and maximum moisture content. So here's ash content for those samples. Again, 224 samples off of trucks as they were being delivered to short-term storage. So very low or relatively low ash content here and relatively consistent ash content. Again, we have pristine samples which tend to have a little lower ash content versus mechanical samples. The ISO standard for Class B wood chips is 3%, so there was a small proportion of samples that exceeded that 3% level here, but it was a very small proportion, and there were no samples that exceeded 3.5% in the harvesting operations that we did. Here's energy content information. So 2 values here on the top. This is all in megajoules per kilogram. Here's the higher heating value. So if you want it on a dry weight basis, so willow is like other hardwoods, about 18.5 megajoules per kilogram dry. If you look at a lower heating value, which includes your moisture content, then this is what we're getting. And so a little more variability because of the variation in the moisture content, but it's about 10 and a half megajoules per kilogram. And this is as received or wet material. Okay, finally, particle size distribution. So this gives you an illustration of the particle size distribution of the willow chips that were coming out of the forage harvester that we were working with, again, in these harvests in 2012 and 2013. The gray bars just show you the percent of the total mass in each of these categories as they went down through a series of screens. And then this is a cumulative bar that shows you the cumulative percent. So 95.5 or 99.5% of the biomass was below 45 millimeters in size, and we had very small proportion of fines at the other end. So less than 3.5% of the biomass was smaller than 6 millimeters in size. So the vast majority of the material is between 6 and 45 millimeters in size. So very consistent material. And in addition to doing this analysis, we had our partners look at it and sent samples to a number of other end users, and when all of them looked at it, the comments back were that this was quality material that they would be happy to be getting at their facilities and would be able to work with. Okay, so that's sort of a summary of the willow biomass quality characteristics that we looked at. Moisture below 50%, ash content is almost always below 3%, and size of chips is very consistent coming out of this forage harvester. There's a whole other stage in this process, what happens with storage and handling. So here's a picture of ongoing harvesting operations in northern New York where the chips are dumped at the edge of the field. And so what happens with this material over time is something that we continue to do work on, and there's questions that need to be addressed in terms of optimizing these systems and minimizing the impact on quality going forward. Okay, so conclusions that there are multiple harvesting systems for willow that are being developed and still being developed. The single pass cut and chip system that we've been working on with New Holland, and there's other forage harvesters in Europe that have built single pass cut and chip systems as well, is working quite well. And in the last 3 years has made significant improvements in terms of the operation of that machine, in terms of, and then also reductions in costs. Okay, so I will stop there, and we're happy to take questions or address comments that people might have.
If you have questions, please feel free to type them in the chat pod, and we'll get to them as we go along. Tim, it seems like most of your evidence really supports the fact that these cut and chip systems are much better in terms of getting consistent quality out of a harvesting operation for willow compared to the baling system you mentioned and the whole whip cutting and stacking. Are there any situations in which you would recommend to maybe an individual producer who has a specific set of conditions to use anything other than this cut and chip system, as in this picture that's indicated here?
So really the limitation with this forage harvester is its size and its cost, right? So there's a substantial capital cost involved in acquiring one of these machines and costs in terms of operating it in the field. So for really small scale situations, it doesn't make sense. For stands of biomass where the yield is low, so certainly below that 45 wet tons per hectare level, it doesn't make a lot of sense to be putting this harvester in the field. So there are those other smaller cut and chip operations. Things like the Baler, where people have designed a system to use the Baler. You can then put those bales into tub grinders, and then tub grinders produce a certain type of material. It's not chips, it's sort of this fluffy stringy material. But if your end-use system, your heating system or whatever it is designed to handle that, and that's the way you've designed it, then those systems work well. If you've got a heating system that's designed to work on chips, feeding tub ground material into it is going to be a problem.
Okay, thanks. We have a question here on wear and tear. So how often do you need to maintain or replace blades in a machine like the one that you have been emphasizing? Any issues with mounting the header on a local harvester to save on transporting costs? I'm just reading this. Sorry. Could you please discuss?
Yeah. So in terms of wear and tear on the machine, there is wear and tear on the blades, and the operator of the machine makes a difference in that. Although on these New Holland harvesters, there's an automatic sensor that keeps the cutting head up off the ground a certain distance, and you can set that and allow the machine to adjust that to keep the head off the ground. That's the biggest problem, is when you run those saw blades into the ground or into obstacles like a rock. So that's the biggest maintenance part of the system, probably. The folks at New Holland actually have found that the internal dynamics, in terms of the wear and tear and the internal dynamics of the forage harvester, so the feed rolls, the cutting drum, the knives inside, that at least for the hours that they've put on the machine to date, there was less wear and tear on the machine than if they were harvesting grass or corn silage. And a big part of that is because the ash content is so much lower than it is for those other herbaceous crops. So there's less wear and tear on the metal parts, on the knives, and on those kind of components inside the machine.
Okay, next couple of questions are related more to logistics. So Zane introduces the idea that you had mentioned in one of the pictures that you showed that in one of your trials it was dry enough, you said you could get a tractor trailer right out into the field. He introduces the point that a lot of this harvest might be happening in the dead of winter, so on frozen ground is it feasible to blow directly into directly into the tractor trailer instead of the cane wagon combination to ease logistics?
Yeah, I think anytime that ground conditions are suitable to put a truck directly in the field, then that makes the most sense. Frozen ground, if you've got very much slope in a ground, putting a tractor trailer on those kind of conditions, it's likely you're going to end up not getting up some sort of a rise. But the people that do those kind of harvesting operations can look at a field and decide fairly readily whether you can put a truck in the field. We had better luck with silage trucks largely because of the small headlands. So with the tight headlands we had in these fields, we did try to put a tractor trailer in the field, and it didn't make it off the headland. It went down to the end of the field and ended up getting stuck on these very small headlands at the end of the field. So that wasn't working in these situations. But anytime you can take a step out of the process and go directly into trucks is beneficial. I'll just comment too, Sarah, I don't think I addressed this issue of can you just move the header around and put it on other harvesters. Yeah, so it'll fit on New Holland forage harvesters, and so you can just move the head and put it on those forage harvesters. Again, a couple of items that sort of people have learned lessons about over time is that you do need to have some sort of a bar or something across the front of the windshield. When you harvest willow, there are stems and branches that tend to slap against that windshield, and eventually you're going to crack it. That's not a cheap thing to replace. And the other place, that's not a hard thing to do. Somebody can just weld up some bars and put them on. It's not like you need something fancy. And then underneath, putting on a plate underneath a forage harvester to protect lines and that are carrying fuel or electrical wires that are underneath that could get caught is the other thing that would need to be done. So relatively simple stuff to do, but the header is built so that you can take it and snap it on any forage harvester.
Thanks. I want to follow up to your point about headlands. There's a question related to that. So Mike asks about maximizing field length. So this would get to the point where you talk about there are mechanical advantages you can introduce to increase efficiency. There are some field design advantages too. So having a good amount of headlands is one, but Mike introduces the issue of minimizing turns by maximizing the length of fields to spend less time in those headlands areas. So he asks about, in the spirit of that question, asking about using riparian buffers, if that would be an appealing option for maintaining some use in those headlands areas. Mike, if I've misunderstood your question, please let me know.
Yep, no, I think that's certainly the case, and I think Justin here with the Eco Willow model has done some playing around with that in terms of field length. So there's a trade-off. Longer field length is generally beneficial until you get to the point where you drive so far away from where you're moving the chips to that the amount of time it takes to turn either your truck or wagon around and get it all the way back to the other end of the field becomes prohibitive. So there is a bit of a balance there, but generally in upstate New York, longer runs are better, and we really haven't run into too many of these situations where it's too long a run. So long linear plantings like riparian buffers, I think have some potential in terms of just being able to get on. And you can envision a riparian buffer being a few rows wide, so maybe you're taking off a couple of rows, you run down one direction, you come back the other direction, and then you're moving on to the next buffer area.
Thanks. Justin just typed in a note for the audience. The woody crops header that fits on the New Holland 9000 series harvesters and the New Holland Forage Cruiser series harvesters. So make a note of that if that was of interest to anyone. There's a question from Gary about just sort of general dealing with a crop like this. So he asks about use of fertilizer to maintain this and maybe some other basic maintenance issues, as well as the life expectancy of a willow plantation.
So in terms of the life expectancy, so if we run on the scenario of 3-year cycles, we can certainly do 7 cycles, so 21 year lifespan of the crop. The crop can go longer than that, but actually this picture is a good illustration. So what happens is you can see this forage harvester straddles one of these double rows of willow. What happens is when this sprouts the next spring, tends to sprout on the outside, and so this double row tends to get a little wider. So this space here is going to get wider, this space here is going to get narrower, and at some point you're going to have a hard time fitting the equipment down in between these two sets of double rows. So that's really the limitation more than a biological limitation. We have trials now on the ground that are in their 7th rotation, and they're still producing well, but they're hand harvested trials, and the space in between them here has become very restrictive. In terms of maintenance, so once the crop is established and after a harvest like this one shown in this picture, you don't need to do a lot of maintenance. It's going to come back fairly quickly. It's going to provide shade and block out most of the weed growth underneath. There's not a lot of that kind of management once you get the crop established. The fertilizer question is still hangs out there a little bit. All the recent trials that we have done on fertilizer has shown that we get no response when we add fertilizer. No response in terms of yield or increase in yield over time. So we have now looked at both organic amendments and just nitrogen fertilizer applications, and at this point are getting no response for the kinds of soils that we've been dealing with. Of course, part of that's a soil issue in terms of what are the nutrients you have available to you on the site. But there's not a lot coming off in wood, right? So the wood that's coming off here is 50% carbon, and then oxygen is the next biggest component. There's a little bit of nitrogen, 0.5% nitrogen content in the wood. There's a little bit of phosphorus, but not large nutrient removals. If you leave the foliage on site, then most of the nutrients are left there to be recycled.
Gary, in terms of life expectancy, another new bio-affiliated researcher, Larry Smart, has also introduced to us several times that in addition to the physical limitation of the actual expanding coppice stumps, at the end of a 7-year cycle, because willow breeding is so advancing so quickly, there might be a much more productive cultivar that you may be interested in planting, or something that's more resistant to a pest problem that you may be having. So those issues too play into life expectancy. It's as much an economic question as it is a physical limitation question. Let's see, what else? Mike follows up asking about storage in general. So in terms of harvesting logistics, there must be a trade-off between the cost of storing material for later use versus transportation costs of moving something directly to an end-use facility. Do you want to address that a little bit?
Yeah, I think every time you handle biomass, there's a couple of things. One, there's an additional cost associated with it, and two, the potential for changing, often in a negative way, the quality of the biomass is a concern. So if you have a system where you can take your material directly from the edge of the field and take it to your end user, then you're minimizing your handling costs, and you're also not going to, you'll have less potential to have an impact on the quality. So for example, if this cane wagon in this picture was to dump directly into a tractor trailer at the side of the road and that tractor trailer went directly to your end user, then that would be, I think, a very good situation. Often the reality is that with a harvester of this size, you can put through a lot more material through, harvest a lot more material, generate a lot more chips than most end users are going to want to be taking on a day in and day out basis if they're blending this material with other sources of wood chips. And so then you get into this issue of needing to do some short-term storage and then delivering it as your end user wants it.
Thanks. If there are any last-minute questions, please type them into the chat box. I'll ask a final question, and if there are others, then I'll follow up with those. But my last question is about the ISO standards for chip quality. What kind of testing would be involved on the part of the producer in terms of frequency or the nature of testing for moisture content and those other attributes that you had listed in order to make sure they're meeting those standards? Or would that be something the producer would want to manage themselves, or something that the end user would want to be looking at more closely?
So that's a good question, Sarah, and I think that's going to be done at this point on sort of more of a case-by-case basis. So if end users have certain standards, if they want to use the ISO standards or whatever other standards they have, then they need to come to an agreement with their producers in terms of who's going to check the material and how that's going to be done. So it's interesting that when you look at these ISO standards, so for example, when we looked at ash content and there was a few percentage of the samples that were above the 3% ash content, we tried to sort out within ISO and asking some questions of people associated with it. Does that exclude everything? I mean, if you have 5% of your loads that have a 3.4% ash content and everything else is below 3, is it just those loads that are excluded? Does everything get excluded? It appears that ISO doesn't set those standards. It's really an issue of with the end user and producer and what the agreements are and what rate of qualifying loads needs to be. Who does that testing? You know, again, is another one of these things that needs to be ironed out, and who's going to do it is going to be the end user, is going to be the producer, and how is there going to be assurance that it's being done appropriately so that both parties are happy. I think those are things that are worked out on a producer-end user relationship. In most of the situations now, there's not a lot of, that I'm familiar with, there's not a lot of testing. There's a lot of looking at material coming off the back of the truck, and people that do it day in and day out have a pretty good idea of whether it's meeting their specs or not in terms of size and moisture content and not having stones and those other kind of things.
Okay. And as a follow-up to that, I mean, in the operations that you've looked at, have you seen Willow Biomass fit fairly seamlessly into markets that have previously been dominated by natural forest or longer woody rotation materials?
Yeah, so it blends well with forest residue materials, particularly situations where people are using residues, so bark-on type material. It's got a higher ash content than debarked clean wood chips is going to have, and so places like the pellet industry where they want that very low ash content, Willow's got a higher ash content than debarked clean wood chips. But in other situations, it blends fairly well into the system. There is a bit of a learning curve, and there is some misperceptions around Willow that take some work to help people get over and understand that, you know, you're really dealing with a hardwood here. It's got the same energy content on a kilogram or pound for pound basis. The moisture content is really not way out of line with other wood chips. It's very similar to what other greenwood wood chips would be. So it's got very similar characteristics, but there is some work that needs to be done with end users to help them to understand that. And I think give them some opportunities to work with small loads first to become comfortable with it and fit it into their system.
Well, thanks so much, Tim. I don't see any other questions. I want to thank everybody for joining us today. You can see Mark and Tim's contact information up here on the screen. So feel free to contact them or visit the New Bio website for any other information. related to these materials. Stay tuned for those events coming up, some of which will focus on a lot of this material that we've gone over today. And Tim, do you have any concluding comments you wanted to make?
Nope, thanks for organizing it, Sarah, and getting the system to run smoothly.
Thanks, everybody.